So next on our agenda is technical talk number 2 of the day from Professor Shreyas Sundaram. Shreyas is the Marie Gordon Associate Professor of Electrical and Computer Engineering and is also co-director of the Purdue Center for Innovation in Control, Optimization, and Networks, also known as ICON. His contact information is in the chat. Shreyas, it's all yours.
Wonderful. Thanks so much, Joel. Can you hear me okay and see my screen?
Yeah, absolutely. Looks good.
Wonderful. Thank you so much. It's a pleasure to be at the symposium again. It's plugging forward, proceeding forward despite the challenges provided by COVID, and still an excellent program. So it's a pleasure to be a part of this. My talk today is going to be about Byzantine-Resilient Learning in Multi-Agent Systems. So broadly speaking, my research group looks at these network systems of agents collaborating to achieve tasks in these complex environments. Particularly what happens when you have agents that don't follow the protocols or the algorithms. How do you design algorithms proactively and still give guarantees of success? So today I'm going to be talking about a general setting and focusing on a specific problem just to illustrate the kinds of ideas and algorithms we've been developing. So consider a large network of agents that are deployed in some environment. So this could be robotic swarms that are exploring some sort of space, a battlefield, or environmental monitoring. It could be smart factories with sensors deployed everywhere, or smart cities. And in general, you've got all these agents representing drones or robots or sensors, and they're all interacting with this environment that they're deployed in. They're all measuring different aspects of it. And each one of them only gets to see a little piece of the overall puzzle. And so the idea is, how do you get them to work together? What information do they have to exchange with each other in order to enable everybody to get a full picture? And there are a variety of challenges that come with this. The network through which these agents communicate could be mobile. The agents could be moving, so the communication links could be changing over time. There could be adversaries in the network. So certain agents may be compromised or may come from untrusted sources, and they may not be necessarily following the algorithm you expect them to. So how do you come up with algorithms that enable all the regular agents, the agents that are following the rules, to cooperatively learn about the environment despite this adversarial behavior? So there are a couple different versions of this problem. Today, I'm going to be focusing on distributed hypothesis testing. I won't be able to monitor the chat carefully, so if there are any questions, perhaps you can save them to the end. So the problem that we're going to be focusing on here primarily for this talk is this idea of distributed hypothesis testing. So the idea is you've got a set of agents, again, deployed in the world. There's some true state of the world. Agents are trying to figure out which of the possible states is the true state of the world, and there may be some Byzantine agents that are trying to lie and prevent the other agents from learning the true state. After I describe our approaches to this problem and kind of the results that we have, which establish the capability to solve this problem, also touch very briefly on the extension to things like resilient distributed reinforcement learning at the end of the talk. So let's start with this, the idea of distributed hypothesis testing. So here's a general setup. So again, we're in some environment, and there's m possible different states of the world, right? So if there's a classification problem, there's going to be m possible things that are going on in this environment. Okay, we don't know which one is the true state, but one of them is the true state. Okay, well, one of these states is really happening. So each of the agents that are deployed in this network, each agent I is getting signals from the environment. It's observing this environment or interacting with it. And so each agent I receives some signal, which we denote SI of t, at each time step t. Okay, and so each agent could have a different signal space. For example, one agent has a thermal camera versus another agent has a RGB camera. The types of signals they may be receiving are different, but they still get some sort of stream of signals. And for each possible state of the world, each agent has a conditional likelihood function. So what does this mean? It basically says, okay, given that this is the true state of the world, what is the distribution of signals I expect to see? Similarly, if that is the true state of the world, what would be the distribution of signals I expect to see? Okay, so all of this is just captured by this function, which says, okay, what's the probability that I see a certain type of signal if this were the true state of the world? And the agents are going to be able to leverage this, or going to want to leverage this information about the distribution of types of signals that they see to cooperatively learn what theta star is. Okay, and so the idea in these classes of problems is that each agent maintains a belief vector, which is just a vector. It's a probability distribution over all the states. right? So that's denoted mu I of t. So agent I's belief over the states at time t is mu I of t. So it could be something like, hey, I think it's 10% theta 1, 30% theta 2, 70% theta 3. Okay, and it's going to update the set of beliefs over time based on the measurements it's getting and information it may get from its neighbors. So the key question in these kinds of problems is how should you do that update, right? How do I incorporate local information with information from neighbors? If I only rely on local information, there may be a limit on what I can do due to the limitations of my sensors and the limited information I'm getting. So I have to talk to other people. But when I talk to other people, first, how should I use their information? And second, I open myself up to misinformation or corrupted information that's injected by those neighbors. So how should I balance those two? Right? That's the key question. How do we design these update and exchange rules that guarantee everybody, all the good nodes at least, learn the true state over time? So hopefully that's the setting is relatively clear. And so the contributions that we've made in the group over the past couple of years is that we've come up with distributed learning rules that guarantee learning and work faster than existing algorithms. So these are sort of best-in-class algorithms, and they also have the benefit of being robust or can be made robust to these kinds of adversarial attacks that are modeled via these typical Byzantine models. So let me give you kind of the overview of how these algorithms work. And it turns out they also have the benefit of being almost embarrassingly simple. Okay, and so here's a simple example for us to wrap our heads around. Suppose that you have a single agent. Let's not even worry about multiple agents for a second. Let's just kind of establish some basic limitations and terminology. Suppose that you have three possible states of the world, right? Theta 1, theta 2, or theta 3. We don't know which one of those three is true. And suppose the agent, the signals that it sees are just coin flips, so heads and tails. And suppose that the signal structure of the agent is given by this matrix here. So what does this mean? It means if the true state of the world were theta 1, the agent is going to see heads 3/4 of the time and tails 1/4 of the time. If the true state of the world were theta 2, the agent is going to see heads half the time and tails half the time. And if the true state is theta 3, the agent's going to see heads 3/4 of the time and tails 1/4 of the time. Okay, so each of these rows is basically that conditional likelihood function that I mentioned before. The probability of seeing a certain signal under a certain state. Okay? And one thing you can notice immediately, just based on the signal structure, is that both under theta 1 and theta 3, the agent is seeing heads 3/4 of the time and tails 1/4 of the time. So imagine you're sitting there and you're observing the sequence of heads and tails, and you're saying, hey, look, heads is occurring 3/4 of the time, tails is occurring 1/4 of the time. I wouldn't know if I'm in world theta 1 or theta 3, right? Because both of those are going to generate that same sequence. But I would know for sure that I'm not in theta 2. Okay. Similarly, if I saw heads 1/2 of the time, I could be pretty confident I'm in theta 2, and I could immediately eliminate theta 1 and theta 3. So this example sort of shows us that there may be certain states that we can eliminate based on the signals that we're seeing just locally, and there may be certain states that we cannot distinguish. Okay, for in this case, states theta 1 and theta 3 are said to be observationally equivalent. Okay, so kind of zooming in on that, right? The probability distributions that tell me what kinds of signals I see under each of those states, that's what's going to tell me the ability to distinguish between those states. The more different those distributions are, the more likely, the easier it is for me to tell those states apart. In this case, the distributions for theta 1 and theta 3 are identical. So from a mathematical perspective, right, this slide looks scary and has a lot of notation. So if you're not familiar with this notion of information theory, do not worry about it. All this is saying is, if I give you two distributions, I want to have a way of coming up with a number that tells me how different those distributions are. Right? Because from a previous slide, we saw we want to be able to see how different distributions are, able to tell apart these states. So there are lots of different ways to do that. One of these things is called the KL divergence, which basically is a function. It's got all these vertical lines, which looks super scary, but all that's happening is it's eating two probability distributions, putting them together and spitting out a number that tells you how different those distributions are. Okay, in particular, if the distributions are exactly the same, then you get a metric of 0 here. And if the distributions are different, you're going to get some positive number saying how different they are. Okay. So in general, for any given pair of states of the world, we say that the pair is observational equivalent from the perspective of a certain agent if the probability distributions of the signals that you see are exactly the same under those two states, or equivalently if the KL divergence between their likelihood functions is 0. Okay. So that's, again, don't worry if that's foreign to you. It's just to establish some basic concepts for people who are familiar with information theory. Okay, So now that we've established this kind of idea of, using distributions of the signals that you expect to see to be able to figure out something about the true states, how do we start incorporating information from neighbors? And this problem's been looked at for some time now, close to a decade, and a variety of rules have been proposed for how you incorporate information from neighbors. And sort of the simplest, earliest approach to do this was the following. Basically, what this says was the following. So essentially, I have local signals. So what I'm going to do is I'm going to take my belief vector, right, my distribution over the sets of states that I think is currently true, and I'm going to use Bayes' rule, right, very basic Bayes' rule from probability theory to do an update of that prior probability into a posterior belief. And then what I'm going to do is I'm going to grab the beliefs from all my neighbors in the network, and I'm just going to average them. So that's all this is saying. So this is saying do a local Bayesian update, grab the beliefs from your neighbors, and average all of those to form your next belief. Okay, so this is called kind of a linear update rule because I'm linearly averaging information from my neighbors. Similarly, other people have proposed log linear rules where you do slightly more complicated operations, but there's still linear averaging in a different space and so forth. And with all of these simple ideas, which is basically, Bayesian update locally, average my neighbor's beliefs, it turns out that under some very mild conditions, it's guaranteed that all the agents in the network learn the true belief, the true state asymptotically, if everybody follows the same algorithm, okay? And there are some very basic conditions. Essentially, for every pair of states, some agent in the network has to be able to tell those states apart based on their local signals, okay? So somebody has to be able to distinguish between each pair of states. Similarly, on the network structure, there has to be a path between each pair of agents. It doesn't have to be fully connected, right? As long as there's a multi-hop path, that's fine. And then conditions on priors, which is everybody should start out believing that any of the states are possible, right? If I start out and I wake up one day and I say, there's no way theta 1 is true, no amount of new information is going to change my mind. So as long as everybody starts out, even with a small prior on everything, that's a condition. Okay, and it turns out that under all of these assumptions, all of these prior works will guarantee convergence, but they all rely on this kind of averaging. Okay, and so the question we started out asking, primarily with a view towards building towards resilience, is first, do we need to do averaging? Is there a different way to solve this problem that actually makes it more amenable to solving in a resilient fashion? So again, let's think about carefully what each agent can do on its own, right? Suppose I forget about talking to anybody else and I just look at the signals that I'm getting and I just use Bayes' rule over time to refine my local beliefs on the true states set of states. Okay, so that Bayes' rule update is just looks like this. Okay, and there's some basic facts that you can establish about this. Just coming back to that example we did with the heads and tails, which I'll show again on the next slide. Essentially, if theta star is the true state of the world, and I consider some other state theta, if theta is not observationally equivalent to theta star, meaning that the distribution of signals that I would get under theta and theta star are different, then eventually I should be able to tell that theta is not the true state of the world, right? Because the signals I'm getting don't match up with the signals I expect to get under theta. However, if theta is observationally equivalent to theta star, meaning these signals have the same distribution from my sensors, I won't be able to tell it apart, right? I won't be able to tell if that's the true state or not. So the key insight here is just by using Bayes' rule, just by looking at my local signals, I can eliminate certain states. I can say for sure that's not looking like the true state, okay? So here's an example coming back to that example that we saw before. Suppose that theta 1 is the true state, okay? And so then the agent is sitting there looking at those local signals, it's seeing how often heads and tails come up. And over time, as it's doing Bayes' rule, it sees that the belief on theta 2 goes to 0, right? It's like, hey, I'm not seeing heads 3/4 of the time. I'm going to have a lower and lower belief that that's going to be the true state. But for theta 1 and theta 3, because I can't tell them apart, they're going to basically even out at 50% probability each. Okay. So that's the key idea. So the key idea is locally, I can eliminate certain states. So everybody in the network can do this, right? So somebody over there can eliminate a certain state from being true. I can eliminate a different state. Somebody else can eliminate a third state and so forth. So the question is, how do we leverage this capability throughout this network for different people, different agents to be eliminating different states to help everybody else converge to the true state? And the idea is very simple. Just use process elimination, right? So if I have eliminated a state, meaning I have a very low belief that that's a true state, I should tell everybody else, hey, I'm pretty sure this is not the state. right? And so what that means is I want low beliefs on a true state to propagate very quickly through the network. What's a way for low beliefs to propagate? Well, you can just use a min rule rather than averaging. So the idea is very simple. Every agent maintains a local belief vector, which is based on Bayesian updating, right? It just looks at its local signals and it's figuring out what's true and what's not. And a global belief or network belief vector, which incorporates information from its neighbors. And it does so by taking the minimum belief for each state from its neighbors. And again, the key idea is that somebody who's eliminated a state will have a low belief on it. If I take the minimum belief, that'll allow me to put a low belief on it and eliminate that state. And that's going to boost everybody's beliefs on the true state up. Okay, so hopefully that's kind of intuitive. Sort of the take home is for each hypothesis, listen to your neighbor that has the lowest belief on that hypothesis. So this is basically the math behind it, right? At each time step, at each iteration, each agent is maintaining two beliefs: a local belief where it never listens to anybody, just is trying to figure out what it can learn based on its local signals, and then network belief, which incorporates the minimum belief on each state from its neighbors. And again, it looks like a lot of math here, but again, just basically on the three simple conditions that we talked about before, for every pair of states, somebody should be able to eliminate it or distinguish between them. Strong connectivity, meaning there's a path from every agent to every other agent, and everybody starts out believing anything is true. This simple min rule update guarantees that everybody will learn the true state asymptotically. Again, as long as everybody is following the correct algorithm. And then this scary-looking expression basically gives a convergence rate. It just says the rate that you discard false hypotheses is going to be exponential. You're going to discard false hypotheses exponentially fast at a rate that's given by the ability of the best agent in the network to distinguish those hypotheses. Okay, I'm just putting it here for people who are quite familiar with information theory and this kind of reasoning. But main takeaway is it works and it works fast. So, and again, this is better than existing algorithms that don't reject this quite as quickly. So here's a simple example, right? So this is a project done with Sandia, and this is sort of still a toy example, but hopefully will kind of illustrate the performance of the algorithm. Suppose you have a bunch of drones that are monitoring a given area, and they're looking for nuclear material being transported through a certain region. Right, so there are 4 cells in this area, and there are 5 possible states of the world. Okay, there's no nuclear material being transported. Nuclear material is being transported through cell 1 or cell 2 or cell 3 or cell 4. Those are the 5 possible states. And so these agents are moving around in their neighborhood. They have sensors at their sensor locations that they're visiting to try and look for signatures of nuclear material. They can talk to other agents within their own cell or to agents in adjacent cells, but they can't talk diagonally. Okay, and so this is the hypothesis testing problem that they're trying to solve. Which of these 5 states is true? So here's a simulation here. And so I'm going to be plotting the belief on the true state, which is theta 2, right? Nuclear material is being transported through cell 2 on 3 different agents in this network here. The red curve is our algorithm, blue curve is, and green curve are 2 different algorithms. And we can see that our algorithm does allow these agents to learn the true state rapidly, okay, faster than existing algorithms. Okay, so that's great. So I told you, look, every day you wake up, you talk to your friends, you take the lowest belief that your friend, any of your friends has on an hypothesis, you use that as your belief and you go from there and everybody's gonna learn. So that's great if everybody does what they're supposed to do, but what happens if some friend of yours isn't following that algorithm, right? Or if they put a very low belief on the true hypothesis without legitimate reason. So here's an example where node 5 or agent 5 at a certain time step becomes malicious or starts acting maliciously and says, I don't want the rest of the network to figure out that theta 2 is the true state, right? I don't want the rest of the network to figure out that material is being transported through here. So I'm going to put a belief of 0 on that true state, theta 2. Well, 0 is the minimum possible belief. Everybody's going to adopt that belief, and very quickly, everybody's belief on the true state goes to 0. Okay, so you can see that this simple algorithm is very easily hijacked, right, by even a single agent that decides to spread misinformation about what's happening in the system. That's not great. So how do we make this resilient to these kinds of adversaries and misbehavior? Okay, the nice thing is that the algorithm is easily extendable to account for these kinds of things. So we're going to consider a Byzantine attack model where each compromised agent in the network has complete knowledge of the system, even potentially signals being received by the other agents. It can act completely arbitrarily. And we're going to assume an F local model. Okay, and an F local model basically says each good guy in the network has at most F bad guys in its neighborhood. Okay, so this potentially allows the entire network to have a huge number of bad guys, right? As long as there are no more than F in the neighborhood of any good node, that's all we need. And the good agents that actually follow the algorithm will be denoted by the set R. So when we have bad guys in the network, there's actually two kinds of redundancy that we need in the system. First, remember that we're trying to distinguish between pairs of states, right? And we need agents that can distinguish between each pair of states. If the good guy compromises all of the agents that can distinguish between a certain pair of states, there's no hope of the other agents being able to distinguish between them, right? Because everybody whose sensors are able to tell those states apart have been compromised. So essentially, you need information redundancy. You need enough agents in the network to be able to distinguish between a pair of states so that an F local set of bad guys can't just take them all out. But that's not enough in this kind of situation. Maybe you do have a lot of agents that can tell apart pairs of states, but if all their information has to get funneled through a bottleneck in the network, that's also a problem, right? Because the malicious attackers could just compromise the bottleneck and prevent all that good information from that huge number of informative agents from propagating to the agents that actually need that information. So you not only need information redundancy, but you need communication redundancy. So you need topological properties that account for both the information structure and the communication network structure. Okay, and I won't go into what that property is in the interest of time, but we introduce a new graph property that we call R robustness, or strong R robustness, to capture both of these redundancy requirements. And if you're interested, you're welcome to look at the paper, or I'm happy to chat with you through email. So here's the idea. So, we've identified the need for redundancy. We've identified properties that capture the necessary redundancy. And here's how we're going to modify the algorithm to make it resilient. So each agent is still going to do its local Bayesian update, right? That never requires interacting with anybody else. So you continue to do that, figure out what you can eliminate on your own. And then when it comes time to updating its network belief, right, which incorporates information from neighbors, if I have fewer than 2F plus 1 neighbors, I'm not going to do anything at that time step. Okay? However, if I have more than 2F plus 1 neighbors, remember in the previous version, I gathered all my neighbors' beliefs and I took the lowest one and I used that and I updated my belief with that. Here, what I'm going to do is I'm going to reject extreme beliefs. So I'm going to look at all my friends' opinions, right, their beliefs on that state. I'm going to throw away the highest F and lowest F and then take the next smallest one, the remaining smallest one. Okay, so instead of taking the minimum value, I'm going to take the F plus first minimum value from my neighbors, and I'm going to use that in my update. Okay, it's very simple, hopefully. And it turns out that under this redundancy condition that I identified, and again, just under non-zero priors and hypotheses, all the good nodes are guaranteed again to learn the true state of the world. And this is going to work regardless of the actions of any F local Byzantine adversary set. Okay, so a very simple tweak where I just throw away extreme beliefs and then use the rest is going to guarantee a huge amount of resilience to potentially a very large number of adversaries in the network acting arbitrarily. Okay, and so this is just an example, again, to illustrate that using this modified algorithm, same setup as before, where node 5 becomes adversarial, sets its belief on the true state to 0. But now, given that all the other agents in the network are suspicious, right? Potentially they're worried about potential bad guys, a single agent in this network has no hope of preventing the others from learning the true state. And so again, with the red curve shows the rest of the agents are in fact converging to a belief of 1 on theta 2. So there are extensions to distributed reinforcement learning. I think, given in the interest of time, I won't go too carefully through this, but in the current setup that we looked at, there were no real interactions with the environment other than observations. But if you have reinforcement learning where agents are trying to figure out how to take actions in order to collectively optimize their costs of taking those actions and control the system that they're all interacting with, then essentially, again, you want them to interact with each other, exchange information about the rewards or costs that they're seeing, optimize sort of this long run cost function. Okay, and so reinforcement learning in general is about how do you update your policies which specify actions to take in any given state over time. Distributed reinforcement learning is how do you do that with multiple agents working together. And in our case, what happens if you have bad guys who are trying to make all the agents learn a bad policy, right, to potentially damage themselves or damage the system. So again, we propose a simple distributed Q learning algorithm that uses this idea of local filtering, right? It throw away extreme values from your neighbors at each iteration, use the rest in an appropriate sense. And so we propose sort of Q learning rules where you use local filtering to mitigate extreme behavior, use consensus type terms to incorporate information from others, and use innovation terms that account for local experiences and local costs. And under appropriate conditions, again, on the network and the adversarial agents and the cost structures and so forth, we can show that this does enable learning. Okay, and that's a paper that'll show up this year at the Conference on Decision and Control. So that is summarized. So, we've developed these resilient algorithms that enable agents in these large scale networks to learn in various contexts despite this adversarial behavior. And these algorithms are highly scalable, right? Very simple operations. They just rely on information from neighbors and very simple filtering operations where I'm ignoring extreme values and so forth. It can tolerate a huge number of adversaries potentially depending on the network structure. And these simple design principles transfer to a variety of learning and optimization scenarios. With that, I will stop. And thank you for listening.
Shreyas, thank you very much. For those who are following that, Shreyas is a link to his homepage, which has his contact information, is in the chat.